If I have multiple resources to multiple processes, then this may be called as process P1. In order to resolve the deadlock, we will go for many other deadlock of prevention and deadlock avoidance algorithms. In Unix operating systems, the deadlock will not occur at all. Hello and warm welcome to one and all. It is Dr. Ravikumar YB, Department of Computer Science, Vidhyaashram, First Grade College, MYSURU, the Temple of Excellence. In today's class, you will learn about the process synchronization problems. That means, as I have already discussed with you in the previous session, that any shared data is to be given access for any of the processes. It has to be protected. Then the data which is residing in the shared memory location is provided with some certain updated information. Otherwise, that leads to an unwanted data that is going to be stored in the shared memory location that leads to an unpredictable results. In order to get an accurate results, we will protect the shared data, also called as a critical section, is protected from all other processes. In order to avoid the unpredictable results from the shared memory location, we will go for the process synchronization. There are certain problems with process synchronization. Let me discuss those problems of process synchronization in today's session. If that is the case, we have the first type of problem, that is bounded buffer problem. The second problem is the readers-writers problem. And the third problem is dining philosophers problem. What is the meaning of this? Also called as the producer-consumer problem. Let me take up the first type of problem, that is the bounded buffer problem. In this case of bounded buffer problem, we have the problem is also called as the producers and consumers problem. The name producers indicates that the producer is going to produce the data. Producers produces the data. Produces the data while consumers consumes the data produced by the producers. Now, a finite supply of containers are available. That means a buffer or a storage locations are available. Now, the producers take an empty container, that means which is vacant in memory location, and fills it with product. Then consumers takes a full container, consumes the product and leaves an empty container. Here what is happening here is the producer is taking the empty container and fills certain data into it, that is the producer, and it is given to the consumer, where the consumer consumes the data from it and in turn gives a vacant buffer to it, so that there is a provision for producing the data into the empty container, and then the filled container is given to the consumer, so that the consumer consumes the filled container and gives the empty container back to the producer. So this process is repeated. If that is the case, the main complexity of this problem is that we must maintain the count for both number of empty and full containers that are available. The problem here is the number of empty containers and the number of filled containers must be tracked and counted here. If that is the case, you shall observe here that this is an empty pool that is taken by the producer. Producer fills it and it is consumed by the consumer, and it gives a empty container to it. That means what? The producer produces a product and consumer consumes the product, but both use one of the containers at the same time. At the same time, it uses only one of the container at the same time, not more than one. Then we have the next type of problem, that is the readers-writers problem. Again, in case of readers-writers problem, we have a shared area of memory locations wherein all the data which is very importantly required is placed here. That means the data is placed here. Suppose if I want to have the reader's ear and the writer's ear, where the readers will read the data from here and the writers will write the data into this location. Suppose if the axis is given at the same time, then there is a problem of process synchronization. So in order to avoid that, there is a data area that is shared among a number of processes. Any number of readers may read simultaneously right to the data area. That means only one writer at a time may write the data area. If a writer is writing to the data area, no reader may read it. Please observe this carefully. We have a reader here, writer here. At the same time, at the 0th second, I can allow n number of processes. That means 1, 2, 3, 4, so on up to n number of processes. N may be 100, 1000, lakh or anything. I can allow all of these processes to read the data simultaneously at the same time. But I cannot allow more than 2 writers to write the data into the same location at the same time. Please make a note of it. We have a reader's ear. Readers are permitted to read the data simultaneously at the same time, while only one writer is allowed to write the data item at that time. That is one situation. Many readers and one writer are allowed. That is one of the option. Which is the next option? The next option is this. If there is at least one reader reading the data, no writer may write to it. That means readers only read and writers only write. A process that reads and writes to the data must be considered as a writer. If that is the case, we have an options like this. That is at least one reader. There may be a possibility of more than one reader. And no writer may write to it. That means when many readers are reading, no writer is allowed. That means at most one writer or no writer is allowed to write at the same time. That is the option you need to understand. Then, which is the next problem? That is DiningPhilosophers problem. In case of DiningPhilosophers problem, there are 5 philosophers. Their job is to think and eat. Think and eat. That's all. If that is the case, we have a chopsticks at the center of these philosophers. This chopstick is shared among these 2. 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 So if that is the case, how can we allow the dining philosophers to pick the chopsticks at the same time? That becomes a conflict again. So if that is the case, the dining philosophers problem is another classic synchronization problem, which is used to evaluate situations where there is a need of allocating multiple resources to multiple processes. That means multiple resources. That means we have a resource 1, 2, 3, 4, 5. This is called as a resource. Resource. If I have multiple resources to multiple processes, then this may be called as process P1, P2, P3, P4, P5. So I may also call these process P1, P2, P3, P4, P5 as philosophers. The philosophers need the resources. That means processes need resources. That's the meaning of it. There are 5 philosophers sitting around a circular dining table. The dining table has 5 chopsticks and a bowl of rice in the middle as shown in the below figure. That means there is a bowl. This is called as a resource. This resource is shared among the 5 dining philosophers, because since they have seated on the dining table, we say that the chopsticks presented here for each of these philosophers are shared, and the data which is placed at the center of the table, that is the bowl of rice, is considered as a resource or data which is called as a critical section, which is shared among multiple processes. If that is the case, we have to allow only a philosopher is either eating or thinking. When a philosopher wants to eat, he uses 2 chopsticks, one from their left and one from their right. That is, one from their left and one from their right. If that is the case, when philosopher wants to think, he keeps down both chopsticks at their original place. During the time of thinking, he places both of the chopsticks on the table. And from the problem statement, it is clear that philosopher can think for an indefinite amount of time. He can think for an indefinite amount of time. It is not a definite time. If that is the case, but when a philosopher starts eating, he has to stop at some point of time. That means the philosopher is an endless cycle of thinking and eating. That means during the time of eating, he can eat only for a definite amount of time. If that is the case, at some point of time, he has to stop eating and place the chopstick on the table. What is that? If there is a chance of this, suppose we have 5 philosophers here, 1, 2, 3, 4, 5 here. When I allow this person to eat, only I can allow this person and this person to eat. If I allow this person to eat, what happens? I have odd numbered person. If I allow odd numbered person, means the philosopher 1, which is the other person I can allow 4th person. Which if I allow 4th person, he picks these 2. If I allow this person, he picks this as well as this. So there is a conflict. At most, I can allow only 2 philosophers to eat at the same time. During the time of thinking, they releases the resource, that is chopstick, and places it onto the table. That is the only solution to the dining philosopher's problem. So, when does the deadlock occurs? A deadlock is a situation in which 2 computer programs sharing the same resource are effectively preventing each other from accessing the resource, resulting in both programs ceasing to function. That means we have this deadlock situation when the same shared data is required for multiple processes. That means resource R1 is needed for process P1, but process P1 is requesting for process resource R2, which is shared by process P2. So the process P2 is waiting for resource R1. In this case, there is a deadlock. If you look at this, I can state this as represent it in the form of a graph. There is a cycle of this graph. If I break this, the deadlock will not occur. If there is a cycle of graph, then we state that there is a deadlock. That means when one of the process is waiting for a resource, the resource is which is held by another process. Another process is waiting for a resource which is held by one of the process. If that is the case, there is a deadlock. In order to resolve the deadlock, we will go for many other deadlock of prevention and deadlock avoidance algorithms. If that is the case, programs are required to specify in advance what resources they need so that they could avoid the conflicts with other programs running at the same time. That means they have to mention in advance that these are the resources required for execution so that there won't be any conflict and there would not be any problems of this synchronization or with the problem of deadlock. If that is the case, eventually some operating systems offered dynamic allocation of resources. That means during the time of runtime, the allocation of resources are done. That means programs could request further allocations of resources after they had begun running. This lead to the problem of deadlock. Here is the simplest example. That is the same thing. Process resource R1 is assigned to process P1 and P1 is requesting for process P2, resource R2. But resource R2 is assigned to P2, but P2 is waiting for resource R1. There is a cycle of graph. If that is the case, there is a deadlock. That means program 1 requests the resource A, which is assigned to resource process P2. Then program 2 requests for resource B and it receives it. So similarly, this situation is called as a deadlock situation. Now, neither programs can proceed until the other program releases a resource. The operating system cannot know what action to take at this point. The only alternative is to abort or stop one of the programs. That means either to abort or to stop one of the process or programs. That is the only one option. Then learning to deal with the deadlocks had a major impact on the development of the operating systems and the structure of the databases. That means how to avoid the deadlocks is a very important thing to understand in case of operating systems. That means data was structured and the order of request was constrained in order to avoid the creation of deadlocks. That means these deadlocks can be avoided with the help of certain algorithms like Banker's algorithm and safe state algorithms. Methods of handling deadlock. Ensure that the system will never enter a deadlock state. How can I ensure that? By using some algorithms. Allow the system to enter a deadlock state and then recover it. That means deadlock recovery algorithms are there. Ignore the problem and pretend that the deadlocks never occur in the system, used by the most operating systems like Unix. That means in Unix operating systems, the deadlock will not occur at all. That means these are the 3 possibilities in which the deadlocks are handled. With this, I am going to conclude my session. Thank you very much. Thank you one and all.